Lab 3, Black Hole Lab. The purpose of this lab is to determine the mass of a black hole based on the observed motion of a star with known mass as it orbits the black hole. Here's what we know. The mass of the star is 1.98 times 10 to the 30 kilograms. We have a CSV file that lists the position of the star at time intervals of 86,400 seconds. We know that the location of the black hole is at the origin, 0, 0, 0. We will assume that the net force on the system, in this case the system is the star, is due solely to the gravitational force of the black hole. Our goal is to find the mass of the black hole. Each row of the CSV file contains the x and y coordinate of the star at a given time. The star's orbit is an xy plane, so we can say that z is 0 at all times. We know that the time interval between each line, delta t, is 86,400 seconds. We can now calculate certain properties for the system. We can use r sub 1 minus r sub 0 over delta t to calculate the velocity for the initial time interval. R sub 2 minus r sub 1 over delta t for the velocity over the next time interval, and so on for all of the time intervals. Next, we can calculate delta v is equal to v sub 1 minus v sub 0, and so on for all of the time intervals. We can calculate delta p sub 0 equals to m v sub 1 minus m v sub 0, and so on for all of the time intervals. Up to this point, we have calculated the properties of the system using the definitions for velocity and momentum. Now we use Newton's second law to say that the net force acting on the system during the initial time interval is equal to dp over dt, the rate of change of momentum with respect to time during that time interval. For delta t small, we can say this is approximately equal to delta p over delta t. Again, we do this for each time interval. We can break dp over dt into its component parts. We find dp over dt parallel by calculating the change in momentum over time multiplied by p hat. We can find dp over dt perpendicular by simply subtracting dp over dt parallel from the total dp over dt. Again, using Newton's second law, we can say that F net parallel is equal to dp over dt parallel, and F net perpendicular is equal to dp over dt perpendicular. If we assume that the net force on the system is due solely to the gravitational force of the black hole, we can say that the magnitude of F net is equal to the gravitational constant times the mass of the star times the mass of the black hole over the magnitude of r squared, where r is the position vector. With some algebraic manipulation, we can say that the mass of the black hole is equal to the magnitude of F net times the magnitude of r squared over the gravitational constant times the mass of the star. Let us run the Python program that will recreate the orbit of the star and show the forces acting upon it. The red arrow indicates F net, which we have stated is simply the gravitational force of the black hole on the star. The black arrow shows F net parallel. The blue arrow indicates F net perpendicular, which points towards the center of the kissing circle. The output window shows the mass of the black hole. This is the value that we're looking for. The mass of the black hole is 1.99 times 10 to the 31 kilograms. What does it mean? How are F net parallel, and F net perpendicular different from delta p over delta t over delta t parallel, and delta p over delta t perpendicular? Over the course of this lab, we have used these equations. The right side of each equation deals with momentum, which is an observable, measurable property of the system. The left side of each equation indicates the total forces acting on the system. Newton's second law allows us to connect the physical qualities of a system, qualities such as mass, velocity, and momentum, to the interactions of the surroundings with the system. This tells us the total forces acting on the system. What if? Imagine a black hole whose mass you found was replaced by a different black hole but still placed at the same location. Assume the motion of the observed star remains unchanged and is affected only by the gravitational force of the new black hole. Could you tell the difference? Since the motion of the observed star remains unchanged, we can say that the new black hole must have the same mass as the original black hole. Think of it this way. We were originally given the mass of the star and the position of the star at time intervals of 86,400 seconds. We also knew the location of the black hole was at 000. Using this information, we were able to find that the mass of the black hole would be 1.99 times 10 to the 31 kilograms. If we now remove that black hole and go back to observing the star, we see that the given information hasn't changed. So if we solve again for the mass of the new black hole, we will still find that its mass is 1.99 times 10 to the 31 kilograms.